Welcome. This is the lecture 29, Dephosphorization of steel. Last lecture we talked about the oxidation of the carbon, silicon, manganese and manganese, and in this lecture we will talk about the oxidation of phosphorus during steel making. Okay, there is the dephosphorization. And the concept cover basically we will talk about the thermodynamics of phosphorus removal, and the phosphorus capacity and this correlation is very important. There is the phosphorus capacity, how much effective the slag is to hold there is a phosphorus into the slag, and how does it correlate with different parameters. Now we discuss about the basic thermodynamics of phosphorus removal, and here basically in steel making, as I said, it is a selective oxidation of impurities over iron. Here what I do, if you want to oxidize the impurities, iron will also get oxidized. It is natural, because when you charge the oxygen into the liquid bath, it is basically the iron is 95% by weight. So by law of mass action, it is the iron that will get oxidized. Okay, then impurity will get oxidized. But if that is the thing we have to think about, that is if we want to oxidize the impurities, and that has to be done in preference to the iron oxidation, because if iron get oxidized, then the yield of the process will be very less. Okay, so we have to see, that is we want to oxidize the impurity in preference to iron, then only our purpose will be served in the steel making. Otherwise, lot of iron will be lost through the slag. Okay, so but as I said, when you charge the oxygen into the liquid iron, oxygen will see only the iron, because 95% by weight is iron. So by law of mass action, it is the iron oxide that will form first, and then the impurity oxidation may take place if they form a much more stable oxide compared to iron oxide, right? If SiO2 is stabler than FeO, or MnO is more stable than FeO, CO is stable than FeO, then this reaction will take place, because in that case silicon will reduce iron oxide to iron, and it itself will oxidize to silica. Similarly, manganese will be oxidized to MnO, FeO will be reduced to Fe, and again C will be oxidized to CO, and Fe will be reduced to Fe. This is possible if all the right hand side oxides are more stable compared to FeO, and actually it is, because before you see from the Ellingham diagram, if you see the silicon oxide, manganese oxide are stable compared to the FeO even at high temperature, and the CO is also much more stable compared to the FeO, okay, at high temperature. So all these right hand side oxides or impurity oxide are basically stable compared to the iron oxide. So even though the iron oxide form first, okay, the impurity will reduce the iron oxide to iron, and they themselves will be oxidized to SiO2, MnO and CO. And then out of this, CO is a gaseous product, so CO will go away from the system. So this reaction will move in the forward direction always, and only thing is that SiO2 and MnO, we have to retain these oxides into the slag, then only this reaction will move in the forward direction. Okay, so that thing will be there, that is in the slag we have to retain them, but CO we don't have to retain it. The slag, it will go away from the system. But anyway, all these three oxides are much more stable compared to FeO, so this reaction will move in the forward direction. Now, but if you see the phosphorus reaction here, if you see the phosphorus line is this one, and iron line is this. This is the P2O5 line, basically P2O5 line, and this is the FeO line. You can find this is the FeO line. So we can find that P2O5 is more stable compared to FeO, right? P2 under standard state, when they are both are pure, when P2O5 is pure, FeO is also pure. Under that condition, P2O5 is stable than FeO. And if it is the case, then it is not possible to make this reaction like this. That is, if I want to do, that is the P2O5, that not P2O5, that is the thing. If I want to make a reaction like this, that FeO plus P, right? If I want to write FeO plus 5 FeO, okay, plus twice P P2O5 plus 5Fe, this reaction is a great no. This will not happen because P2O5 is much more stable, that is, what is this? Yeah, that is Fu is stable, right? Sorry, Fu is stable than P2O5. P2O5 is less stable, right? Since it is upper in the Ellingham diagram, P2O5 is less stable. Since P2O5 is less stable compared to Fu, so this reaction is not possible, right? So that's why it is said that it is difficult to oxidize phosphorus selectively over iron under the standard condition. Because Ellingham diagram, all oxides, metal and oxides are pure. So under standard condition, it is not possible because Fu become more stable compared to the P2O5. Now fluxing helps in lowering the phosphorus line under non-standard condition. Now if I do the fluxing what will happen? Then P2O5 and calcium oxide, basically if I give some calcium oxide, then they make a very strong compound with the P2O5. So as a result, the fluxing will help to reduce the activity of P2O5 significantly. Okay, that is possible. So under non-standard condition, what we are doing, there is that 4 by 5P, this is the reaction, phosphorus plus oxygen forming the P2O5, and equilibrium constant you can write like this. And now activity of phosphorus, considering the phosphorus is pure, activity will be 1. Now I am not considering P2O5 is pure because I have added flux. So P2O5 now reacted with the flux, means calcium oxide, and it forms a compound, a strong compound, tricalcium phosphate. It is a strong compound. Okay, as a result, its activity will go down. If its activity go down, then its PO2 has to come down because the K, equilibrium constant, is at a particular temperature, it is constant. Okay, so if you reduce, now it was initially it was pure P2O5, so activity was 1. Now if I flux the slag, that means if I add some amount of lime, then it will react with the P2O5 forming calcium phosphate. As a result, activity of P2O5 is decreased, will be decreasing. If it decreases, then PO2 has to decrease because K is constant at a particular temperature. So then what happens, the delta G naught, what happens, is equal to RT-ln of PO2. Since PO2 is decreasing, your delta G naught is decreasing. So basically, apparently, this line, these are called the apparent P2O5 line under non-standard condition, non-standard state, because when P2O5 is not pure, okay, when the activity of P2O5 is less, then this line will come down like this. And these two lines basically represent the basicity of the slag. Depending on the basicity, if it is a basic, it is a highly basic slag, then the line is this. Comparatively less basic, this is the line. Okay, but that is the activity of P2O5 has decreased. As a result, this line, that is the phosphorus line, have come down here. So when the phosphorus line come down here, then P2O5 becomes stable compared to Fu, and then you are able to remove the phosphorus in preference to iron. So this is called the selective removal of phosphorus. So for all other oxide like silicon, manganese and carbon can be removed under acid slag condition. That is when the slag is not basic, even you can remove them because these oxides, impurity oxides, are stronger compared to, that is the more stable compared to the iron oxide. Iron oxide is less stable compared to them, but it is not the case with respect to P2O5. When P2O5 is pure, then P2O5 is less stable compared to Fu. But when you flux P2O5, then its activity decreases, and then P2O5 become more stable compared to Fu, and you can selectively remove the phosphorus over iron. This is a very, very unique concept. So if you want to remove the phosphorus, a basic slag is a must. For removing silicon, manganese, carbon, basic slag is not a must. But obviously, the silicon removal will be much faster in presence of basic slag because silica also form a very strong compound with the calcium forming dicalcium, tricalcium silicate. As a result, activity of SiO2 go down, this reaction will move further into the forward direction. So basic slag obviously helps the silicon oxidation or the silicon removal, but it is not a must because silica itself is more stable oxide compared to the iron oxide. Okay, but in case of the manganese, it is not the case. In case of manganese, is a basic oxide, so basic slag doesn't help much. But in manganese oxide itself is a very strong, stable oxide compared to the FeO. So manganese also you can remove under steel making condition. Okay, so if you have more oxidation power, so FeO activity is more, you can remove manganese in the form of MnO. Okay, that is possible. And for carbon, it is not a problem at all because CO is a gas, so it go away from the system. And since CO is a stable oxide, so absolutely carbon removal not a problem. So, but if you want to remove the phosphorus, you have to flux the P2O5, okay, or you have to make a basic slag such that activity of P2O5 decreases and it can be selectively removed. So, this point I am hammering, this is a very important point. That is why everywhere you see BOF process, basic oxygen furnace. So, oxygen you are giving, but basic is important. Unless you make the slag basic, you cannot remove the phosphorus. So, that is an essential thing for phosphorus removal, right. Okay, so now you can see activity of P2O5 in slag at different temperatures, and the slag is defined, that is the in terms of different combination of summation of basic oxide with some weighting factor, different weighting factor, like for CO we have taken a very high weighting factor, and then manganese oxide, and then MnO, then FeO, and then SiO2, SiO2 acidic oxide. So, this is the way the slag composition. With the slag composition, activity of P2O5 how it varies, and this is the way it has been defined, and you can find that activity really decreases with increase in basicity. As the slag basicity increases, activity also decreases, and also it is a function of temperature. So people has done lot of activity calculation at basic slag condition at different temperature. Effect of FeO on the dephosphorylation. You can see this is the reaction. Now, this is the phosphorus reaction you can find. You have to add CO, then only this reaction move in the forward direction. Tricalcium phosphate it has formed, and you can see one thing is that higher FeO and CO both favors. You can see if FeO increases, oxidation potential slag increases, then this reaction move in the forward direction. If CO increases, then also this reaction move in the forward direction. So, both FeO, higher FeO and CO both favors this reaction. Then what will do? But thing is that if you increase the FeO, then CO become diluted into the slag, and if you increase the CO in the slag, then FeO get diluted. So, both the things are there. So, but a higher value of one in the slag dilutes the other, that is very important. An optimum amount of FeO should be required, okay, that does not dilute the CO also too much, the slag basicity. So, an optimum CO is required for that if you want to remove the dephosphorylation maximum extent. That is, this is basically you can see there is weight percent of this is weight percent of, that is the phosphorus partitioning, the percentage of P2O5 into the slag divided by percentage of phosphorus into the metal. This is the way the phosphorus partition coefficient, okay. And now phosphorus partitioning increases, you can find with increase in the FeO, but there is an optimum FeO. Everywhere you can find there is an optimum FeO. Here the basicity is more, that is why your partition ratio become high. There the basicity is increasing. This line low basicity 2.4 and then 2.8 and 3.5 basicity. So, with increase in basicity, partitioning becoming high, but at the same time you can see with increase in the FeO also. Initially when the FeO increases, partitioning is increasing, but beyond a certain point again the partitioning is decreasing. So, a percentage around 15 to 20%, 15 to 20% FeO is found to be very good, okay. That is the 15%, around 15 to 15% is good for the dephosphorylation, and optimum FeO is required. And dephosphorylation now you can write in terms of the ionic theory. You can write like this: phosphorus, and then FeO you can replace by dissolved oxygen, okay. And the basic oxide, there is a CO you can represent in ionic theory, you can represent in terms of the oxygen ion concentration, okay, activity of oxygen ion concentration. And right hand side basically the tricalcium phosphate, you can write the phosphate ion is this thing basically 2PO4 3 minus. In ionic theory it assumes there is the all complex anion and the anionic system is there, because everything exists into the slag in the form of anions, okay, anions and cations, nothing exists in the molecular form, okay. So, that way in the ionic theory I can represent the phosphorus reaction in this way. I can write the equilibrium constant this as a ratio of the activity of product and the reactant, And partitioning, dP we can write in this form, percentage of phosphorus into the slag by percentage of phosphorus into the metal, and in terms of K prime. K prime basically some constant time of K, and that is equal to into activity of oxygen to the power 5 2 and activity of O2 minus 2 to the 3 by 2. Now, what are the favorable force for dephosphorization? There is the partitioning ratio. How do you can increase the partitioning? One is the basic slag, mode is the basicity, oxygen and activity, mode will be the, and then optimum Fu in the slag, that is the oxidation potential of the slag, okay, and also the low temperature, because K is inversely proportional to the temperature. So, if temperature is high, then your if temperature is low, K is high, so dP is high. So, at low temperature it will be favored. Phosphate capacity is a very important parameter, is basically defines, that is the capacity of the slag to hold the phosphorus. And how do you define it? You can see it is defined, there is the partition coefficient of phosphorus divided by activity of oxygen. That means it is partition coefficient is normalized with respect to the oxidation power of the slag, because if the oxidation power is high, dP will be high obviously. So, if you normalize it, then only the effect of base will come into picture. You can find dP by A by, that is the activity of O, you can write in terms of, that is the equilibrium K prime square into activity of oxygen. So, you can find that is the KPO now is a function of basicity of the slag. So, the phosphate capacity of the slag is a function of slag composition or the slag basicity, okay, and it is basically a function of slag basicity. This is the KPO. This is the holding capacity of phosphorus of the slag is defined by this term. So, it depends on the composition of the slag or the basicity of the slag. So, at a particular oxidation power of the slag. So, if your oxidation power is constant, then KPO depends on that parameter only. KPO depends on the basicity of the slag. But that is why let us correlate this, the KPO with the basicity. If we want to correlate it, you can find that there is hardly any correlation, but it is supposed to increase with increase in the basicity KPO, but hardly any correlation, no correlation can be observed here. And with respect to temperature, if you see KPO versus temperature, there is a very unique correlation. Temperature, KPO also depends on temperature. So, you can find a very unique correlation, but you do not find any correlation with the basicity. Therefore, that is the phosphorus capacity does not correlate with the common basicity. This is the common basicity, that is the summation of basic oxide divided by the summation of acidic oxide. If I take, then KPO does not hold any correlation. What does it mean? It means all the basic oxides are not equally efficient to retain the phosphorus in the slag. Only few oxides, basic oxides are there who are responsible for retaining the phosphorus into the slag, not all the basic oxides. Otherwise, it could have hold a very good correlation, no correlation at all. So, let us see, that is why later on this correlation, there is a phosphate capacity correlates with the BO. BO is a specially defined basicity of the slag, or you can say basic oxides. If you consider only the percentage of CO, percentage of CF2 and also 30% of MgO, that is the 0.3 of MgO percentage. That means MgO is also good for phosphorus removal, but not as strong as CO and CF2, but 0.3. Whatever the percentage of MgO, you take the weighting function is 0.3 only, where that the weighting function here is 1 and 1, here it is 0.3. So, MgO is little less strong compared to Cu and CF2 for dephosphorization. But you can see it is much better than MnO, FeO, because MnO, FeO do not, as a basic oxide, they do not have much role in the dephosphorization. MnO, FeO, they do not have, because this correlate very nicely with this composition only, CO plus CF2 plus 0.3 of MgO. And this direction, this is basically the your phosphate capacity, this is the phosphate capacity. So, you can see it is a very nice correlation, and this is taken from a different temperature data and from different literature and from different, and all of them holds a very nice correlation when I defined the basicity in terms of BO, where we consider only the percentage of CO plus percentage of CF2 plus 0.3 of MgO. MgO also very effective, but not as like CO and CF2, but it is also very effective. And while MnO and FeO are not very good as basic oxide. So, for at least retaining the phosphorus, the approximate dephosphorization power ratio for some cations has been estimated as this thing. So, this is been basically calculated from the equilibrium correlationship. So, and then you can find that is the cation as a cation Ca2 plus is 30,000 times more effective in removing phosphorus compared to the Fe2 plus ion, right. Similarly, MgO is 1000 times greater than that of FeO and Mn is 3 times that of the Fe. So, Fe2 plus. So, calcium cation, calcium ion is most powerful as far as the dephosphorylation is concerned and followed by your Mg. The result shows the decisive role, that is the decisive role of CO, CF2 and MgO in the phosphorus capacity of the slag. So, holding capacity depends on the CO, CF2 and MgO in the slag, then only the slag will be able to able to hold the phosphorus into the slag without reversion. And this is basically shown here, basically the phosphate capacity, if you can draw and percentage of this, they very nice correlation. Compared to that, there was absolutely no correlation when we used all basic oxide to acidic oxide. So, there was no correlation, but here it is correlation. So, it clearly indicates that CO, CF2 are the more primary basic agent or the who plays the decisive role in retaining the phosphorus into the slag. Okay. So, this is the phosphorus and reference, and the conclusion we can say that is the selective phosphorus removal is only possible under basic steel making condition, right. So, you can remove the carbon, manganese and silicon even under acid steel making condition, although the basic slag favors the silicon removal, that is different thing. But if you want to remove the phosphorus, okay, over iron, that is the selectively to remove the phosphorus, then you have to have a basic slag. This is the first thing. Second is the phosphorus partitioning become maximum at an optimum FeO, because both FeO and CO favors the phosphorus removal, because FeO act as an oxidizing agent and CO act as a basic agent. Okay. So, if you increase both, it is supposed to increase this dephosphorylation, but because if you increase more amount of FeO into the slag, then CO get diluted. Okay. And so, it has been found that is the 15% of FeO in the slag is good for dephosphorylation, okay, optimum. And phosphorus capacity, it is very important, does not correlate with the common basicity, where you consider all the basic oxide responsible for dephosphorylation. If you consider that, then in that case we do not get any correlation at all with the phosphate capacity. And phosphate capacity perfectly correlates with some another definition of basicity defined by BO, basic oxide, where we consider percentage of CO plus percentage of CF2 plus 0.3 of percentage of MgO, because these are the only 3 oxides who are responsible for dephosphorization. And manganese oxide is also there, but manganese oxide is not equal as compared to the FeO, CO and the CF2. And MnO and FeO has no role to play as far as the retention capacity of the slag is concerned for the phosphorus. Okay. But FeO obviously plays a role as an oxidizing agent. Okay. So, that thing has to be cleared out. So, FeO plays a role as an oxidizing agent. So, if you increase the FeO, there is the phosphorus removal, the phosphorus oxidation is favored, just like by increasing the CO also. But FeO's role is as an oxidizing agent, and the CO role as an basic oxide, as an constituent for holding the phosphorus into the slag. Okay. Thank you very much.